Hello ladies and gentlemen, welcome to my video. This is today's question, pretty challenging one. It cannot be solved using common integration by parts or substitution. We have to use Feynman integration tricks, which is differentiate inside the integral combined with the Euler formulas. First step, define a function j with parameter a and b, which is almost the same to the question Q, but the e power negative ax instead of e power negative x, while sin bx instead of sin x divided by square root 3, which means q is equals to j when a equals to 1 and b equals to 1 over square root 3. Apply partial differentiate over dA for function JAB. For the integrand in the right hand side, before partial differentiate, let's expand it to two parts. Part number 1, sin bx divided by x. Part number 2, minus e power negative ax multiply sin bx divided by x. The left hand side can be simplified as j prime ab equals to integral 0 to infinity. There is no a in the part number 1, so differentiate over a equals to 0. For second part, there is a which is e power negative ax. Meanwhile, sin bx and x are constant. Differentiate e power negative ax will cancel the negative and cancel the x. Next, Euler formula e power I theta equals to cosine theta plus I sin theta, where I equals to square root of negative 1, which is imaginary number. When theta equals to bx, we have e power ibx equals to cosine bx plus I sin bx. We need the sin bx only, so therefore the j prime ab can be rewrite as im and then integral 0 to infinity e power negative ax multiply e power ibx dx, where im stand for imaginary part. We can combine the integrand become e power negative x and then multiply a minus ib. Other part remain the same. This is integratable, which is equals to negative e power negative x multiply a minus ib, and then the whole thing divided by a minus ib. We know e power negative infinity approaching 0 and e power 0 is 1. Therefore, we obtain im 1 divided by a minus ib. We cannot leave it in this form. We need to multiply a plus ib divided by a plus ib, which is equals to im a plus ib divided by a square plus b square, which is equals to b divided by a square plus b square, because we only need the imaginary part. From here, we can obtain JAB by performing integration to the j prime ab and then dA, which is equals to integral b divided by a square plus b square dA, which is equals to b divided by b multiply inverse tangent of a divided by b plus constant c. Of course, the b divided by b can be removed. How do we find the constant c? Okay, let's recall the first equation that we defined at the beginning of the video, which is also JAB. This is the one here. In the case that a equals to 0, the j that we found just now give us j a equals to 0, b equals to inverse tangent of 0 divided by a plus c, which is equal to 0. How do I know it is equal to 0? We can get that 0 from the j that we defined at the beginning of this video, which is j equals to 0b equals to integral 0 to infinity 1 minus e power 0 divided by x multiply sin bx dx. Because e power 0 is 1, 1 minus 1 is always 0. Compared to j for a equals to 0, give us a constant c must be equal to 0, which gives us j parameter a and b is equals to inverse tangent of a divided by b. At the beginning of this video, we define q equals to j, a equals to 1 and b equals to 1 over square root 3, which gives us inverse tangent of 1 divided by 1 over square root 3, which is inverse tangent of square root 3. That brings us to the conclusion of this video. The final answer of this question is equals to pi divided by 3. Thank you for watching this video until the end. Please continue support my channel, subscribe, give a like and share my video in your social media. See you tomorrow for more video. Bye bye.